13. Before we go and discuss the main topic for today, let me try to finish the second order ODE case. And today we look at some nonlinear second order ODE. Okay, so I'll just briefly discuss some tricks which you can use to solve some second order linear ODEs. Okay, so first, so these are just some methods to solve completely nonlinear. So they are solved nonlinear second order. Okay, so the first method, we are going to look at the equations of the form f t x prime x double prime is equal to 0. So that is there is no first order, there is no x in the equation. That is, there is no function dependent. That means there is only the f is just function of t x prime and x double prime. There is no x in this case. Okay, the trick what you use is you substitute z is equal to x prime, then this will imply that z prime is equal to x double prime, and the equation becomes f t z z prime equal to 0. So this is first order ODE. Assume you can solve it. And assume that you get a solution z is solid and z is some function phi of t and a constant c, right? This is a constant, undetermined constant, because you will integrate. Okay, and then you, to get the solution x, you basically integrate basically this phi t comma c dt, plus you'll get on one more constant c. Okay, so this is how you solve these kind of equation. Okay, so basically you have to just remember this. All right, so if there is no x in the equation, then this is the way to do it. The second method, the second trick, is that here you have no explicit t dependence, so we are going to consider equations of the form something like this. Okay, so no t dependence. Okay, of course x is a function of t here, so there is a dependence on t but via x, not directly. Okay, so the trick here again is the same what you did in last case. You write z is equal to x prime. Okay, and what we'll do is that we'll convert this ODE, which is consist of derivative with respect to t, into ODE which consists derivative of z with respect to x. Let me see, let me show you how to do that. Note that now x double prime will be equal to dx prime by dt, which is equal to dz by dt, which is equal to dz dx dx dt. Okay, which is equal to z, because this is equal to z, so this will be z dz dx. Okay, so with this this what we get is a new ODE, but but with respect to x. So we get x here, and this will be z, and that second derivative, this part, this is equal to this thing. So what you get is z dz dx is equal to 0. Now you solve, assuming we can solve this. Okay, then you'll get again z as a function of x now. Okay, now to get the solution x, you will need to solve now. Not that you will get dx, sorry, not that. You have to do the dx by dt is equal to phi x comma c. Okay, so first you have to solve for z. Okay, from this you will get z, and from there you need to solve another first order ODE. Okay, so solve this. So we need to solve two first order ODE. Two first order ODE. Okay, and of course assumption here is that you are able to solve all of them. Note that this is not that hard to solve, because there is no dependence of t, so you can write it, you can do it by variable separation. Okay, so this is trivial to solve in some way, provided you can integrate it with respect to x, 1 upon this of with respect to x. Okay, so this is not that hard to solve. The last method is again very interesting. Here we look at a completely nonlinear second order equation, but there is assumption, and assumption says that f is homogeneous. Let me explain what I mean by that. We say f is homogeneous function of degree k. Of course, k is an integer, positive integer. Okay, degree k with respect to variables x, x prime, x double prime, if ft of lambda x prime, lambda x double prime is equal to lambda power k f t x, x prime, x double prime for all lambda in R. Okay. All right. So now, if this is the case, then f is called homogeneous function of degree k, and then the trick here is that we substitute x prime is equal to xz. Okay. So of course this means that more precisely x prime t is equal to xt and zt. Zt is some again unknown function. We will derive the equation for zt. Okay, once we solve for the z, then we can plug it in here, and then you can solve for the solve a linear equation for x prime, for x. Okay, so let us see what happens when you substitute this. Then what you get is that x double prime is equal to x prime z plus x z prime. Okay, But x prime here, you have x prime, but x prime is equal to xz, so this will be equal to xz square plus xz prime. Okay, and now we can substitute both these expressions, this expression and this expression, in our ODE, and then what you get is f t x xz xz square plus xz prime is equal to 0. Okay, now assuming we can solve this, this is a first order ODE, but assume we can solve this. Okay, no, sorry, they still dependent on x. I cannot just do that. Okay, so now note that this is okay. I should be careful here now. I cannot still solve that because there is x and z both. I just need it for x, but this is by homogeneity, and we have not used the homogeneity. Will be equal to x power k f t 1 z square plus z prime. Okay. So 1 is anyway, you can it doesn't matter what is this 1, and this is okay. So with this you get the new equation, let's call it f tilde, which will t z square plus z prime is equal to 0. And now we solve f tilde t z z square plus z prime is equal to 0, and this assuming we can solve this, then you get z as a function of t with some constant dependence, and then you solve it phi x comma c, sorry, not x, is t, this is t, comma c x. Okay, and this is a linear first order order, and you can solve this. Okay, so basically you have to use this homogeneity, that f is homogeneous, this trick, and
Excuse me, sir.
just 1 second, and then you can do this. Yes, tell me.
Sir, lambda can be a variable also, because in this case we are taking x to be, isn't lambda a constant?
It's just a function. It doesn't
Okay, so
matter what is lambda.
okay.
I mean, I'm not taking any derivative or anything that you worried about is a constant or something, right?
Okay, sir.
If I'm taking derivative in the definition of homogeneous function, then we need to worry about it. But there is no derivative or anything, right? So whether it's a form, x is some value, right? You put a value, you get a new value. And this is true for every lambda in R. So it will be true for x power x also, right? Okay. So just remember this. If you remember this, so if this is true, then you get it this way. Okay. So these were some tricks which probably will be helpful to you if you want to solve second order equations ever. And then this is the way to solve them even if they are fully nonlinear. So far we did only linear cases. Okay. With this, the methods are complete, and we are going to now go to a little bit more mathematical problem, which is called Sturm-Liouville eigenvalue problem. Okay, so it's a completely new topic. So let me start with the headlines. So we are going to look at Sturm-Liouville eigenvalue problem. Okay. So clearly it will be similar to the eigenvalue problem you have seen for the linear algebra. That means there will be a linear transformation, and linear transformation we are going to discuss the eigenvalue of the linear transformation. Only thing here is that linear transformation will be a differential equation. Okay, differential operator. Okay. So to start with, we'll going to look at boundary values problem. So we are not going to look at initial value problem, we are going to look at boundary value problems. So more precisely, we look at x double prime plus at x prime. So we look at basically linear second order ODE. But in addition to that, we have a lambda, which will come, I will come back to that later on. Ctx is equal to 0, so it's homogeneous. But with the initial condition 0. So these are called boundary conditions. So instead of initial conditions, we will have now boundary conditions. Okay. Here lambda is some parameter. It is allowed to change, and for different lambda you will get different solution, and we will see for what lambda what happens. Okay. So that will be the interesting. So the lambda will be the interesting part here. So our interest is to choose lambda such that the boundary value problem has a non-trivial solution. In general, you can immediately see it as trivial solution, right? If you put x is equal to 0, this is a solution. But we are not interested in those trivial solutions. We are interested in a non-trivial solution. So we want to choose lambda such that this problem has non-trivial solutions. And that will be very well connected to the eigenvalue problem for a linear transformation, because not that you were only interested in lambda such that Tx is equal to lambda x, and x has to be non-zero. If x is x0 automatically satisfies that, right? Recall that if T is a linear transformation and V was a vector, then this was always satisfied if V is equal to 0. But we are not interested in that. We are interested in V not equal to 0 vectors. So similarly here we are interested in non-trivial solutions. So we want a non-trivial x. We want to choose lambda such that we get a non-trivial solution to this problem. And we'll do some examples to clarify what I mean by that. Okay. Now first, a small exercise which you should do is that we can convert this equation, boundary value problem, into a much simpler case. How? Instead of having first order term, we can get rid of first order term, and this we have done it already once, but I will repeat it again. So let us multiply both sides of OD, other side is 0 anyway, with the function Pt is equal to exponential of integral as ds 0 to t. Okay, or a to t. Okay, and then you do some manipulation. What you will get is then ODE is converted into following form: P, and then this is the same P, this PT, okay, x prime and whole prime plus lambda qt xt. You have to find what is q, plus r x xt. So RT xt, okay, is equal to 0. And now that these terms are pretty much same, we can combine them together. So in the end, we will be only interested in the following form. In the form p t x prime plus lambda q t x is equal to 0. Here we always have p is a positive function, strictly positive function, because it's exponential function, as I showed you. Okay, and of course p is continuously differentiable, so it's c1 on open interval ab. Okay, if I write closed interval here, that means the one-sided derivative is continuous. Okay. Okay. So in general, we will just write open interval, but it's well understood when I write the closed interval that the derivative from left and right are the one which considered at the boundary. Okay. So and of course we will have a boundary condition. So this kind of problems are called Sturm-Liouville eigenvalue problem. And the interest here, so this is eigenvalue problem. What is the eigenvalue problem? Find lambda and non-trivial x such that ODE and the boundary conditions are satisfied. So here you can look at it from your linear algebra point of view. If you write T as a linear transformation which applied on, let's say, C2 function, so x is C2AB, that means continuously these are the functions which are second derivative exists and is continuous on closed interval AB, and with the xa xb is equal to 0. Now if you consider this set, this is a vector space. On this you define a linear transformation from this to itself such that T of x is basically p t x prime x prime. So this is a linear transformation, linear operator. This is actually a linear operator because it will map the, okay. So let's linear operator. Okay, and now you want to find what are the eigenvalues of this operator. So what you do, you write it equal to T of x is equal to lambda x. Okay, and then this will be basically saying that P of x prime is equal to lambda x. Q has to be taken care. So let's, this is another function q. Okay. Okay. So this is pt x prime, and then you have to take care of this q. So you want this to be equal to lambda qt x, and this is combined together. So this lambda will depend on q. Okay, so this is very similar. Of course, if you take q to be 1, then it's exactly the case of linear operator what you study in the linear algebra. But otherwise, it is there is a bit of weight here, q, which you carry, which you keep it here. Okay, so what we'll be interested in this, basically finding x such that, okay, of course there is a minus sign here, so this is minus sign. This is just adjusted in this. So we are interested in finding such lambdas basically. Okay, so this problem is converted into this finding the solution of ODE. Okay, so this is very standard thing to do for ODE if you are interested in some very nice solutions. Okay, Then, of course, if for in general for lambda, you'll always have one solution which is a trivial solution, which is x is equal to 0. But we are not interested in that solution. What we are interested in a non-trivial solution. So if let us define now. If there exists lambda, and I will write q. Q of course depend on sorry, lambda depends on q, because q is a function. So if there exists lambda such that and non-trivial function x in C2 AB and satisfy boundary condition such that Pt x prime plus lambda q qt x is equal to 0, then lambda q is called eigenvalue of, let's call it star, and x will be corresponding eigenfunction. So this is very similar to the eigenvalue and eigenvector. Here you have eigenvalue and eigenfunction, because the vector spaces consist of functions. Okay. So now what we'll be interested in is studying of these eigenfunctions and eigenvalues for this problem. Okay, that is what we will be interested in. Let us look at some examples so that and you should realize that this is not something I'm just talking from the theoretical point of view. There is indeed a genuine interest in these things, and then we'll study their properties. Okay. So to start with, let us look at a very simple test case. If you take minus x double prime is equal to lambda x on let's say open interval 0 1 with the initial condition x0 is equal to boundary condition something like this. Okay. And lambda is constant. You know how to solve this problem, right? This is a constant coefficient case, and you know how to solve all the problem. So we'll go one by one. When case 1, we'll take lambda to be less than 0. In this case, what happened? Your solution will be xt. The general solution will be C1 e square root of this will be square root of minus lambda t plus C2 exponential minus of minus lambda square root of t. Not that lambda is negative, so minus lambda is positive. Okay, so this will be a general solution. Now, as soon as you put x is equal to 0 and x1 is equal to 0, this will combine, implies that C1 is equal to C2 equal to 0. Okay, so lambda less than is equal to 0 less than 0 cannot be eigenvector, cannot be an eigenvalue. Because for all such solutions which satisfy the boundary condition, you get a 0 solution, right? If you put C1 C2 equal to 0, this will be 0 function. Okay, so lambda less than 0 cannot be an eigenvalue. Similarly, if you look at the case 2, we take lambda equal to 0, this cannot be an eigenvalue. You know what to do in this case. Now case 3 is interesting. as we'll see, let us look at lambda positive, and then you look at the solutions lambda x. Then the general solution for this case from the theory what you know is C1 sine of square root of t plus C2 cos of square root of t. Okay. Now, if you put u0, sorry, x0, why am I writing u0? Okay. So let's x0 is equal to 0. What you get? You get C2 equal to 0. Okay. So that means the solution is okay, and similarly when you put x is equal to 0, this will imply that basically C1 is equal to 0. But note that this is not the only options. In this case, note that these functions, they never vanish. For any value of lambda, they never vanish. But here there are certain values of lambda for which they vanish, and there is a possibility that for those I can take some C1 and C2 so that will so that these conditions are satisfied irrespective of C1 and C2. Okay, so if you do that, then let's take a appropriate value here. I want to take value such that this value is 0. Okay, so if you look at lambdas such that this is equal to 0, then you get square root of lambda is equal to no, I need to satisfy the boundary condition, so not this way. So what I will do is I want sine square root of lambda t at t equal to 1 to be 0. So this means I get sine of square root of lambda is equal to 0. This means lambda square is basically n pi. Sorry, square root of lambda is n pi. Okay, this implies that lambda is n square pi square. So note that when lambda is n square pi square, I can take the solution xt equal to sine n pi t. Okay, and this will be my solution. All right, agree? Because note that clearly it satisfies the ODE, right? It satisfies the ODE. And if you look at x0, this is sine 0, so this is 0. x1 is sine n pi, which is 0. So, and note that this is non-trivial. Okay, but this will only work for n lambda equal to n square pi square. So that means now I have a eigenvalue and eigenfunction. So what are my eigenvalues? So lambda is n square pi square such that n is equal to 0, not 0, 1, 2, 3, and then correspondingly I will have a eigen function xt is equal to sine square root of lambda t. Okay, so this is my solution to the eigenvalue problem. I have eigenvalue and eigenvector. Okay, is this fine with all of you? That only when lambda is positive I have the eigenvalues. Yes.
Yes, sir.
Yes.
Okay. So similarly, you can repeat the same exercise for another test case, a little bit different, but nevertheless, you can see that what I'm doing. If you look at x double prime plus lambda x is equal to 0 with xa, xb is equal to 0. Okay. And okay, so and you look at the now what I have done is that instead of domain 0 1 I have domain a and b. So when you do that, your eigenvalues will be lambda is equal to lambda k, you can say, is equal to or lambda n, you can say, it doesn't matter, k square pi square b minus a square. So there is a scaling factor. This is the scaling factor when you go from a domain 0 1 to ab. Okay, so you get this additional scaling for the eigenvalues. Eigenvector will be same, just lambda square root of lambda of this. So this you take square root of this. Okay, so there are indeed and normally these problems are very important when you have some oscillatory behavior in the situation. Not that in this case we have oscillatory solutions. Okay. Now, as for the case in the linear algebra, here also we will now study some of the properties of these eigenfunctions. Okay. So first result and the proof are very similar to the linear algebra case, but with a small twist. Okay. And the twist will be clear as soon as I write the statement. Let phi1 and phi2 are two eigenfunctions. Okay, of star with respect to eigenvalues lambda 1 and lambda 2 with lambda 1 not equal to lambda 2. Then integral 0 to 1 or integral a to b, I should write, a to b q of t phi1 of t phi2 of t dt is equal to 0. So note that if you go back to the problem and if you assume that q is positive, so far I have not assumed that q is positive, but if you assume that q is positive, then the integral, this kind of integral are nothing but inner product. Okay, for any function f to be positive, integration of f x1 x2 imposes an inner product structure. Okay, and what this says is that phi1 and phi2 are orthogonal with respect to that inner product. Of course, here I am assuming that q is positive, but for this proof, for this particular statement, they need not be the case. Okay, and of course, but as a consequence, phi1 and phi2 are linearly independent. Okay, so let us look at the proof, and proof is fairly easy. It's exactly what you do for the showing that two vectors are orthogonals corresponding to different eigenvalues will be orthogonal with respect to certain inner product. Okay, but here is much easier because you already know that inner product. So phi1 and phi2 are eigenfunctions. Okay, so that means p x prime, sorry, not x prime, phi prime, because phi 1 prime plus lambda 1 q phi 1 is equal to 0. Similarly, p phi 2 prime plus lambda 2 q phi 2 is equal to 0. Okay, I will multiply this with phi 2 and this with phi 1. and let's see what happens. Then this becomes integral of p phi1 prime prime phi2 plus lambda 1 q integral a to b integral a to b lambda 1 q1 q2 dt is equal to 0. So I multiplied and took integration with respect to this, and now I'll throw this integral here, so derivative on this one, because boundary conditions are all 0 for both phi1 and phi2. So only thing I'll get is integral a to b p phi1 prime phi2 prime dt plus integral a to b lambda 1 q phi1 phi2 dt is equal to 0. Okay. All right. So now similarly for this thing I get integral a to b p phi1 prime phi2 prime dt plus integral a to b lambda to q phi1 phi2 dt is equal to 0. Now these terms are equal, so I can subtract one from another one. So I get only these terms will be left. So these will get cancelled out. So what I will get is implies that lambda 1 minus lambda 2 integral, they are constant, lambda 1 lambda 2 a to b q phi1 phi2 dt is equal to 0. Now lambda 1 is not equal to lambda 2, so this is not equal to 0, so that means this is equal to 0. So this implies integral q phi1 phi2 dt is equal to 0. Okay. Now let's go back to the linear independence proof. So we have proved the integral is 0. Now their linear independence is trivial. We assume phi1 is equal to constant multiple of phi2 if they are linearly dependent. Okay. Then this integral becomes c q phi1 square dt is equal to 0. Now phi is not a trivial function, so this cannot be 0. This is not 0, so this integral will not be 0. So that means c is 0, but that is a contradiction. So this is a contradiction. Okay. So phi1 and phi2 are linearly independent. Okay. Now with that in mind, all right. Okay.
Sir?
Yes.
How did you take out that p from the differential? Because p was a function of t.
I did not take it out. I never took it out.
So here it was in the integral, right?
Okay, let me show you how to do. So this is p phi1 prime phi1 prime phi2, right? Okay, it was something like this, right?
Okay, sir, got it. Oh, okay.
We took derivative, this take it this one here. So you get okay. So now I want to show few more results, and not all of them will be proved because proving them becomes quite tricky. But one thing some small results can be proved, and I'll prove that. So one result I have proved already. The second result which I would like to prove, and you can follow, you should try to prove it yourself because it's not that hard, and it's exactly follow on the lines of this previous theorem, which says that if qt is positive, strictly positive, okay, then the eigenvalues, note that eigenvalues depend on Q of star are strictly positive. Okay, that you should try to prove. It's exactly on the same line of what I did, but you have to just see that. Basically, what you have to do is that let's assume lambda is an eigenvalue, and then you have to show that it's strictly positive. Okay, so proof, if you want, I can show you some steps. So because assume lambda is an eigenvalue. Okay, then integral of a to b p xt prime whole prime. I'm going to multiply this with xt itself, dt plus integral lambda q xt square dt. So here x is a eigenfunction of lambda. Okay, this will be equal to 0. This is just follow from the definition. You do integration by parts and use boundary conditions. Then this side, if you bring it here, integral a to b, it will be p x prime dt, okay, which is equal to integral p, so there will be a negative sign, and like here, right, there is a negative sign here. So there will be negative sign here, minus p x prime square dt. So this is always going to be negative because p is positive and x prime square is positive. So this is negative. And now you look at this side. If q is positive, this is positive. So this has to be positive. Okay. So this implies that lambda integral a to b q xt square dt has to be positive. This implies lambda has to be positive. Okay, so I gave the complete proof. Now it's not okay, so we'll stop here for the timing and we'll continue in tomorrow's class, and tomorrow I will finish this topic. I will also upload a tutorial related to some of these problems. The tutorial might contain some additional things which will be done probably later on, but there will be lots of problems related to this topic. Okay, and this will come in the exam. As I told you, the syllabus cover which will be covered till tomorrow will come in the exam. Okay, so for the timing I'll stop here and I will upload these notes now itself so that you can have time to go through it. Okay, I stop the recording and then I take your questions.